It's the excuse me. This is the continuation of the introduction to 3.4. You can either study this in the book on your own, or you can use this video. I'll leave it up to you. These are just the example 4, and you can see, just do the reciprocal operations to isolate the term with the variable in it right here. So add 4 to both sides, divide both sides by 2. And then, so you have an exponential form in which 3 is the base, 2t minus 5 is the exponent, and the product is 15 over 2. So we can put it, we can take the log of both sides, is one way to do this. So we'll take both sides of the equation and turn them into products of the log with the same base and with the same base. So we're doing log base 3 with product 3 to the 2t minus 5 and log base 3 to the product of 15 over 2. And this is the meaning of the term taking log. When you say you're taking a log of both sides, that means you're taking both sides and turning them into products of the same log base. So this is an okay reciprocal operation. Now, what do I do next? Well, log base 3 of product 3 raised to the power of 2t minus 5 equals 2t minus 5. Since the log base 3 of product 3 raised to the first power equals 1, raised to the power of 2t minus 5 equals 2t minus 5. Over on the right side, I use the change of base formula to convert the log base 3 to log base 10. So I got the log base 10, that's the invisible base, of product 15 over 2 divided by the log base 10 of 3. So using the change of base formula. Now this can be evaluated on the calculator, but we won't do that yet. Instead, we're going to isolate t, since that's our goal. So I'm doing reciprocal operations, adding 5 to both sides and dividing both sides by 2. And I now have this complex fraction here. T equals the log of 15 over 2 divided by the log of 3 plus 5, and then the whole thing divided by 2, which is approximately equal to 3.417. So let's just go through the steps here. Open parenthesis, you can see it right here on the screen. Log 15 divided by 2. Notice my usage of parentheses to keep numerators and denominators together. Divided by the log of 3, close parenthesis, divided by 2, plus 5, I'm sorry, plus 5, close parenthesis. Okay, so that's the whole numerator part here, okay, divided by 2. Now, let's go, and we're going to use our answer. This is what t equals, and we're going to put it back into the original equation. So we're going to go back up to the top here, and we're going to use the calculator to do this. Okay? So we're going to do 2 times 3 raised to the power of, and then we're going to open parenthesis, 2 times the answer second minus, that puts the answer in, 2 times the answer minus 5, close parenthesis on the exponent, okay, and close parenthesis again, we got 2, 2, 2, 2, okay, minus 4, and that should equal 11. And it does. Okay, so we know our answer is all right. Okay, so then the book wants you to do 218 number 65. Now you can either do it on your own, and then come back and check your work. Why don't you do that? You can scroll back up in this thing if you want, or whatever. Or you can just follow along here. And you can see the reciprocal operations as in the previous example to isolate 2 to the 3 minus x equals 113 over 5. Okay. Then take the log of both sides. That is, make 2 to the 3 minus x and 113 over 5, both of them products of logs of base 2, since we have a 2 here. And so we get log base 2 of product 2 raised to the 3 minus x equals 3 minus x. On the right side, we use a change of base formula, since we don't have a log base 2 in our calculator, although some of you may. Just as in the previous problem, we have this complex fraction, and we end up with, we multiply both, we subtract 3 from both sides, we get negative x, we multiply both sides by negative 1, we get x equals 3 minus the log of 113 over 5 divided by the log of 2, approximately equal to negative 1.49825. Again, let's do this in the calculator. 3 minus the log, open parenthesis, 113 divided by 5, close parenthesis, divided by log of 2, and what did I do wrong? I got one too many parentheses in here. Let me go back up here and delete this. Okay. All right. Go back to the original problem. This part is really important. I can't make you show this to me on a test because you do it with using the calculator. But you really want to do this for yourself. The one thing I want you to see is that it doesn't take very long. So 5 times 2 up. So you really want to practice this as I'm doing it. 3 minus second answer. Close parenthesis, minus 13. And we get 100. Okay. Next. Example 5, solving an exponential equation in quadratic form. All right, we got e to the 2x minus 3 to the e, 3 times e raised to the x plus 2. Now what they want you to do is recognize that e to the 2x raised to the power of 2x is the same as e to the x raised to the second power. So, which is an example of here of the property a raised to the power of b raised to the power of c equals a to the b times c. So e to the 2x equals e to the x squared minus 3 times e to the x plus 2. Well, we're now in quadratic form. We got squared. This is a trinomial of degree 2, and then degree 1, and then degree 0. So we can factor this into e to the x minus 1 times e to the x minus 2 equals 0. Okay? If you multiply this out, you'll see that it will work out. We'll have e to the x squared, which is what e to the x times e to the x is going to equal e to the x plus x, e to the 2x, or e to the x squared, minus e to the x minus 1 e to the x minus 2 e to the x gives you minus 3 e to the x, and then negative 1 times negative 2 equals plus 2. Okay. So then you take the two factors and use the zero products property to evaluate them. E to the x minus 1 equals 0, e to the x equals 1. So x equals 0. And then e to the x minus 2 equals 0, e to the x equals 2. And then we're going to take we're going to take the log of both sides. So ln of e to the x equals ln of 2. X equals ln of 2. So this is log base e of product e to raise the power of x. So that becomes x equals natural log of x, as natural log of 2, which is 0.69. 3147, and then we here is where I get here's where I check it. So I take ln of 2 and plug it into the original equation up at the top here. Okay. And then number 71. Again, you can do this on your own. And then check it here if you wish, or you can follow along. E to the 2x minus 4 times e to the x minus 5. E to the 2x becomes e to the x squared minus 4 times e to the x minus 5. We're now in quadratic form, and we factor this into e to the x minus 5 times e to the x plus 1 equals 0. E to the x equals 5. We take the log of both sides, natural log of both sides, and so we get x equals ln of 5, which is 1.61. You get that on your calculator. Ln of 5, 1.609. And then here I plug it in to check the answer. So here's one solution. X equals the ln of 5. Now, the other one is e to the x plus 1 equals 0. E to the x equals negative 1 does not exist. There is no power you can raise e to in which it will equal a negative number. So remember, the domain for e to the x is going to be x is greater than 0. Okay. All right. Now, 213, solving log equations. And they talk about exponentiating each side. Okay, so you have ln of x equals 3. So now we got equations with logs in them, and then turn both sides into the equation of the same base, which is convenient for the inverse property. So we got ln of x equals 3. So we'll exponentiate each side and turn each side of the equation into an exponent that has the same base. So we take the ln of x and make it the exponent of e, and we take 3 and make it the exponent of e. We still have an equation. We've really changed things, okay? E raised to the power of the log base e, which is ln, of product x is going to equal x, and e to the 3 is a number which we can evaluate on the calculator. So x equals e to the 3, which you can then... Okay, so here's example A. Ln of 3x equals 2. E to the ln of 3x equals e squared. 3x, so e raised to the power of ln of 3x is going to equal 3x. So 3x equals e squared. X equals e squared over 3, which is 2.463 approximately. If you've seen the checking techniques, you can start using them. Okay, B, a little bit more involved. Log base 3 of 5x minus 1 equals log base 3 of x plus 7. Exponentiate both sides. We'll use the we'll make both sides an exponent of base 3. And we get 5x minus 1 equals x plus 7. 4x equals 8, x equals 2. And then we check it just by plugging it back into the original equation. Number 93. Exponentiate both sides. So we have ln of 4x equals 2 plus 1. E to the ln of 4x equals e to the 2 plus 1. 4x equals e to the 2 plus 1. X equals e to the 2 plus 1 over 4. Okay. There's more. Another example, solving a log equation. Do reciprocal operations until you've isolated the log with the variable in it. So the log of x equals negative 1/2. Exponentiate both sides. E to the negative 1/2 equals e raised to the power of ln of x. X equals e to the 1/2. I skipped that step in here. Let me put that step in. Okay, there's that missing step. All right. So x equals e to the negative 1/2. I haven't bothered putting that. You can do that yourself in the calculator and then check it. And so here's number 97. Do reciprocal operations to isolate ln of 3x equals 19 over 2. Exponentiate both sides. E to the ln of 3x equals e to the 19 over 2. 3x equals e to the 19 over 2. X equals e to the 19 over 2 divided by 3. And we get a pretty big number. Again, check it. Okay. Example 8, solving a log equation. More stuff. Isolate, exponentiate. 3x equals 25, x equals 25 over 3. Don't forget to check. Number 99. Isolate the log. Okay, so we have the log base 4 of 0.6x equals 12 over 7. Exponentiate. And since it's base 4, we make since the log base 4, we use base 4 for the exponent. So we have 4 raised to the power of log base 4 of 0.6x equals 4 to the 12 over 7. 0.6x equals 4 to the 12 over 7. X equals 4 to the 12 over 7 divided by 6 equals 17.945. Okay, example 9. Checking for extraneous solutions. This is important. Okay. ln of x, ln of x minus 2 plus ln of 2x minus 3 equals 2 ln of x. Okay, we combine the products. Ln of x minus 2 to the 2 times 2x minus 3 equals ln of x squared. Now, let me... x minus 2 times 2x minus 3 is 2x squared minus 7x plus 6. Now, we have two logs that equal each other. They have the same base. If that's the case, then the products must be equal. So now this is a solution that we could have used in earlier steps instead of exponentiation. So you got two logs that equal each other. Log equals log. They have the same base. Therefore, their products have to be equal. So we can then just simply make an equation out of the two products. So 2x squared minus 7x plus 6 equals x squared. X squared minus 7x plus 6 equals 0. X minus 6 times x minus 1 equals 0. So x equals 6. X minus 1 equals 0. X equals 1. Now 1 is not valid since the ln of 2 minus 3 equals negative 1. Logs can't be negative. Ln of 6 minus 2 plus the ln of 12 minus 3 equals 2 times the ln of 6. Ln of 4 plus the ln of 9 equals the ln of 36. That works out. Okay, so we had an extraneous solution of x equals 1, whereas x equals 6 was okay. All right, so number 109, same thing. Okay, we got ln of x plus 5, blah, blah, blah. So we're going to combine these two logs on the right to be, so we have ln of x plus 5 equals ln of x minus 1 over x plus 1. X plus 5 equals x minus 1 over x plus 1. So we make the products equal. We got two logs of the same base equaling each other. Therefore, the products must be equal. So we have x plus 5 equals x minus 1 over x plus 1. Multiply both sides by x plus 1. X plus 5 times x plus 1. We get x squared plus 6x plus 5 equals x minus 1. Make it all equal to 0. We get x squared plus 5x plus 6. We get x plus 3 times x plus 2 equals 0. So we get the ln of negative 3 plus 5 equals the ln of negative 3, negative 5, minus the ln of negative... Now, the ln of negative 3 minus 5, that's ln of negative 5. Boom, that's out. That's no good. All right? So, negative 3 is no good. And if we put in negative 2, we're going to get over here in this term, ln of negative 2 minus 2, that's ln of negative 4. That's out. Not to mention these two are out as well. There are no real solutions for 109. Okay, page 215, example 10, prove the change of base formula. You just need to go through this to study it. Prove the log base a of x equals the log base b of x over the log base b of a. So, first step, let y, we're just picking out y, equals log base a of x. Okay, notice that that is this left side of this equation. Exponentiate, a to the y equals x. Okay, exponentiate. So in other words, we're putting this log equation into exponent form. A to the y equals x. A to the y equals x. Take the logs of base b of both sides. Log base b of a to the y equals log base b of x. Okay, so we simply took these two sides of the equation and made them products of the log with the same base. Now, we're going to use turn the exponent of the product on the left side into the coefficient of the log. So log base b of a to the y equals y times log base b of a equals log base b of x. So y equals the log base b of x. Now we divide both sides by the log base b of a. So we get y equals the log base b of x divided by the log base b of a. And now we substitute log base a of x, which we set up right here, for y. And we get the log base b of x equals the log base b of x over log base b of a, which is the change of base formula. And then in problem 113, you're asked to do the proof again. Prove, now you're doing it for base E. Okay, and you can just go through this and study it. Example 11, approximating the solutions of an equation to 3 decimals, and use the graphing utility. So we got the ln of x equals x squared minus 2, make the whole thing equal to 0, and put it in the graphing calculator. So you got x squared minus 2 minus ln of x. Now the thing you have to mess around with is the window. So you can see my window here, and you can see my graph, and then I use the I use the calc function, second trace, and all of that to find the two zeros. Okay, now 119 is a little bit trickier, problem 119. You got log base 10 of x minus x cubed minus 3. Okay, make the whole thing equal to 0. Bring these guys, x cubed minus 3, over to the left side. So you got log base 10 of x minus x cubed plus 3. Put this in the calculator. But this graph is really, you have to really mess with the window. And you can see the window that I've got here, x max, and the scale and everything. It's really very small in order to see these zeros. So, and I have to completely change the window and see in order to see the 0 on the left versus the 0 on the right. So you can look this over. And anyway, this is how I get my, so here's a 0.001 and the other one is 1.4685. So that's something you just have to work with. Okay, doubling an investment using continuous growth. A equals principal, amount equals principal times E raised to the RT. 1,000 equals, now, how long will it take us to double $500 continuously compounded at 6.75% interest? So we make the equation 1,000, which is doubled, equals 500 times e to the 0.675t. Divide both sides by 500. And then take the log of both sides. So the ln of 2 equals 0.0675t. T equals the ln of 2 divided by the rate of interest, which can sort of be a general formula. And so t equals 10.688. So about 10 years, a little over 10 years. Okay. Double and triple at continuous compounding. So here's for $2,000. You can see it comes out to the same thing. ln of 2 divided by the rate of interest equals t, 9.242. It's not going to matter how much money it is tripling. Okay, 3,000 equals 1,000. That's 7.5. Doesn't take long at this rate of interest, which is unheard of, but whatever. Okay. All right. Example. So what problem number was that? That was a problem number. Did I write it down? I did example 12, but I don't know what number this was. Anyway, but this is some number, and you can look it up in the textbook, what number that is. Okay. All right, example 13, the average salary for public school teachers. So here's a model for predicting. So the average salary in thousands of dollars is approximated by negative 2.983 plus 15.206 times the natural log of t, where t is years. T and the domain of t is between 5 and 27, where t equals 5 represents 1985. So when will the average salary be $45,000? So you just make y equal 45 and then start doing your stuff. And do reciprocal operations until the ln of t is isolated. Okay? And you end up with the ln of t equals 47.983, 15.206. So you take the, you convert to exponential form. Okay, now we're in log form. So we're log base e of product t equals this exponent. So we're going to write t equals base e raised to the power of 47.983 divided by 15.206. Okay, and you can do this in one step. This is not hard to do in the calculator, and you get 23.465. Don't forget to check. Okay. And then page 219, number 149, number of banks, Y, 1999 through 2009. All right. The domain is 9 through 19, where 1990 is 0, and t equals 9 represents 1999. So they want to know when there will be 7,100 banks. So you plug it in. Do the same thing as you did in the example. You end up with ln of t equals 7,100 minus 13,107 divided by negative. You can read it. Put it in exponential form. So it's base e. E raised to the power of this number right here equals t. T equals. Now let's just go over how you do this in the calculator, since I did not show. I don't know why I didn't show that. So let me clear this out here. So it would be simply second ln. And now the numerator, you have to put that in parentheses. 7,100 minus 13,107, close parenthesis, divided by negative 2077.6, close parenthesis. All right, let's double check. So we do second ln to get e up here with an exponent. Now we're going to put the numerator in parenthesis. So we got to do another parenthesis. 7,100 minus 13,107, close parenthesis for the numerator. Then start the denominator, which is simply negative 2077.6. We hit enter. And we get 18.017. So the year will equal 1990 plus 18, around 2008. And that is that. Now, I will post this document on Edline, so you can see the document on Edline as well.